Hi, my name is Michael Pendazis, and this is Math 231, Linear Algebra Chapter 3. This is online lesson number 3. So last lesson, we finished 3.2, and we talked about orthogonality in 3.3. And in this lesson, we will finish 3.3, and then we will talk about 3.4, which is the geometry of linear systems. So let's get started. Okay, so the very last thing we talked about last lesson was the projection theorem. Okay, and so it was theorem 3.3.2, and we're still talking about 3.3 now. And so theorem 3.3.2, which is the projection theorem, was the following. If U and V are in vectors in Rn, so if U and V are vectors in Rn, and A does not equal 0 as a scalar, then U can be written in exactly one way as U equals W1 plus W2, where W1 is a scalar multiple of A, and W2 is orthogonal to A. Okay, so that was the projection theorem, theorem 3.3.2. Okay, and so then I also wrote down these two vectors you're trying to find. W1, which is the projection of U onto A, is equal to U dot A over the norm of A squared times A. And that's the vector component of U along A. And W2 is U minus the projection of U onto A, and that's equal to U minus that value we have over there, U minus U dot A over the norm of A squared times A, and that's the vector component of U orthogonal to A. Okay, so we have our vectors W1 and W2 there. So that's the projection theorem. That's how you find W1. And that's how you find W2. And so in a problem like this, you might be given a vector U and a scalar A. So you might be given a vector U and a scalar A, and you have to find W1 using this formula. You have to find W1, which is this, then you have to find W2, which is that, and then U is just equal to that W1 plus that W2, and then you will have found how to write U as the sum of those two vectors. Okay? So that was the last thing we did last class, right? And the picture from last class, if we have a vector, let's say A here, and let's say we have a vector U here, then our W1 would be this vector. And geometrically, that would be W1 and W2. This would be W1, and that would be W2. And when you add them, it equals U. So here, U equals W1 plus W2. Okay? Okay, so that was what we did at the end of last class, and so we're going to use all of that to answer the next question. So in this exercise, we're going to use that. So this is exercise 5 in 3.3. So exercise 5 is let U equal to vector 2, negative 1, 3. A equal to the vector 4, negative 1, 2. Find the vector component of U along A and the vector component of U orthogonal to A. Okay, so that's the example. So the vector component of U along A, that's W1. And the vector component of U orthogonal to A, that's W2. And so U is equal to W1 plus W2. There's exactly one unique way of doing this, with W1 and W2 satisfying these conditions. Okay, so let's do that. So the formula for W1, the vector component of U along A, is W1 is equal to U dot A over the norm of A squared times A. And so what we need to find, U dot A, we need to find the norm of A, and then square it, and that's it, and then we just plug in A. So we need to calculate U dot A and the norm of A, and then plug them in how we need to in that formula to find W1. So U dot A is equal to the dot product of these two vectors, which is 2, negative 1, 3, dotted with 4, negative 1, 2. And this is really easy to compute. You just take 2 multiplied by 4 plus negative 1 times negative 1 plus 3 times 2. So we're just multiplying corresponding components of these 3 tuples. And so this is equal to 8 plus 1 plus 6. That's equal to 15. So U dot A is equal to 15. Okay, so this is 15. And now the norm of A here, the norm of A is equal to the square root of the sum of the squares of A, which is 4 squared, plus negative 1 squared, plus 2 squared. That's 16 plus 1 plus 4. That's equal to the square root of 21. Okay, so now the norm of A is equal to the square root of 21. So now U dot A is 15, norm of A is square root of 21. And so now you just plug that in. And so U dot A is 15 over the norm of A, which is square root of 21 squared, times A, where A is the vector 4, negative 1, 2. Okay, so now the square root of 21 squared is 21. So this is 15 over 21 times this vector. And so then 15 over 21 is 5/7, and this is 5/7 times 4, negative 1, 2. And this is 20 over 7, comma, negative 5 over 7, comma, 10 over 7. And so now W1 is equal to that. Okay? We need to find U dot A and the norm of A, and you just plug it in. You square norm of A in the denominator, right? And so you just plug in A, and then you're multiplying this by 15 over 21, that's multiplying it by 5/7. And so you just multiply each component by 5/7, and you get that vector. So W1 is equal to that vector. Okay, so we found W1. So I'm putting a check there. We found the vector component of U along A. And then to find the vector component of U orthogonal to A, that's W2. Okay, so this was W1. So W1 was equal to 27, comma, negative 5/7, comma, 10/7. So that's W1. Now we're going to find W2. Okay. So W2 is the vector component of U orthogonal to A. And so this is just U minus W1. And so that is just U minus W1, which is 27, comma, negative 5/7, comma, 10/7. And this is equal to 2 minus 27, which is negative 6/7. Negative 1 plus 5/7, which is negative 2/7. And then 3 minus 10/7, which is 11/7. So W2 is that vector. Okay, so now we found both W1 and W2, and we're done with example 5. Okay, so next, let's note that U dotted with W2, because W2 is the component of U orthogonal to U. This is orthogonal to U, right? Our definition earlier. And so what should happen is its dot product should be 0. And so if you test that, if you plug in U, so if you plug in U, which is 2, negative 1, 3, and you dot product it with W2, which we found was negative 6/7, negative 2/7, and 11/7. If you dot product those two vectors, then what you will get is negative 12/7 plus 2/7 plus 33/7. Oh, sorry. Okay, sorry. When you take, what I want to say is that we're going to make W1 dotted with W2, because in the picture you have A, you have U, you have W1, you have W2, and so what's orthogonal is W1 and W2. Okay, so we're going to check that. And when we check that, we get 20/7, comma, negative 5/7, comma, 10/7, negative 6/7, negative 2/7, 11/7. And so when you dot product those two answers, you'll get negative 120 over 49 plus 10 over 49 plus 110 over 49, and that's equal to 0. Okay? And so we get the result that the dot product of W1 and W2 is 0. That means that they're perpendicular or orthogonal. Okay, good. Okay, so that's the end of that thought. So the norm of the vector component of U along A is the norm of this. So U dot A over the norm of A squared times A. And so the projection of u along A is that. And so we're going to find the norm of that. And so then this is equal to, well, so u dot A is a real number. And so that's the absolute value of u dot A. And it's divided by the norm of A squared still, times now the norm of A. And so this is equal to the absolute value of u dot A divided by the norm of A. Okay? And so this is equation 12. And so the conclusion is that therefore the norm of the projection of u along A is equal to the absolute value of u dot A over the norm of A. Okay? And this is equal to the norm of u cosine times the absolute value of cosine theta. That's equation 13. Okay, and so the norm of the projection of u along A is equal to the norm of A times the absolute value of cosine theta. And that's because u dot A is equal to the norm of u times the norm of A cosine theta. And so that, right, and that would imply that the absolute value of u dot A is equal to the norm of u times the norm of A times the absolute value of cosine theta. Okay, and that would imply that the absolute value of u dot A divided by the norm of A would equal to that thing divided by the norm of A. And so this thing and this thing would cancel, and that's equal to that. Okay? And so this is equal to that. See? This is equal to it. Okay? So this is equal to this, and this is equal to that, so that's equal to that. Okay, and we're relying on the definite when we talked about the dot product, the u dot A is equal to that. Theta is the angle between u and A, right? So if here's u and here's A, and we take the initial point of u and A and we put them at the same point, theta is the angle between those two vectors. That's the theta in that equation. Okay, so the next theorem is theorem 3.3.3. Theorem of Pythagoras. Okay, so it's called the Theorem of Pythagoras in Rn. Okay, and so if u and v are orthogonal in Rn, with Euclidean inner product, then the norm of u plus v squared is equal to the norm of u squared plus the norm of v squared. That's equation 14 in 3.3. Okay, so this is theorem 3.3.3, Theorem of Pythagoras in n space. Okay, and the Euclidean inner product, remember, the inner product is not one specific function, it's a function with properties, which we'll talk about later. But the Euclidean inner product specifically is the function that takes u dot v, and it's equal to u1 v1 plus u2 v2 plus dot 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 plus un vn, where u and v are vectors in n space. Okay? So that is the Euclidean inner product of two vectors, u and v. And the Euclidean inner product of u and v is u dot v is equal to that. where first component of u times the first component of v plus the second component of u times the second component of v plus dot 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 plus the nth component of u times the nth component of v. Okay? And so you're using that definition of the dot product in order to define the norm, and so that means that the norm of your vector is the square root of u dotted with itself. Right? And so, okay, so we're using that definition of dot product, and we find the norm of a vector by taking the square root of u dotted with itself. And so that would be the norm of u. The norm of v here would be the square root of v dotted with v. The norm of u plus v would be the square root of u plus v dotted with itself. So u plus v is a vector. You're adding u and v and you're getting another vector. And so the norm of u plus v is the square root of u plus v dotted with u plus v. Okay, and so we get this equation holds. Okay, so that's the theorem of Pythagoras in n space, okay? And so now I'm gonna get better at keeping this board straight up. Good, okay. So now theorem 3.3. Okay, so part A, in R2, the distance d between the points P naught and X naught, comma Y naught, and the line AX plus BY plus C is equal to 0 is capital D is equal to the absolute value of AX naught plus BY naught plus C over the square root of A squared plus B squared. That's equation 15 in 3.3. Okay? And so the distance between a point and a line. And so if you were to look at a picture of that, if you had a line here, if you had a line capital L and you had a point P naught here, and X naught, comma Y naught. The distance would be the length of the line segment in this example would be the length of this line segment. That would be D. Okay, so the distance from a point to a line is the length of the shortest path you take from that point to get to any point, some point on that line. And so the shortest distance to go from this point to this line is if you went along the line segment perpendicular to the line and you went to this point on the line, because this point on the line is closer to that point than any other point on the line. Okay, part B. In R3, the distance capital D between P naught, X naught, Y naught, Z naught, and the plane AX plus BY plus CZ plus D is equal to 0 is capital D, which is the absolute value of A X naught plus BY naught plus CZ naught plus D divided by the square root of A squared plus B squared plus C squared. And that's equation 16 in this section. Okay, so all of that is theorem 3.3.4. It tells you a formula for the distance between a point and a line and a point and a plane. So this illustrates part A, how you can find the distance from a point to a line, and then this picture illustrates part B. If you have a plane, so if you have a plane like this, right, here's your plane, and then let's say you have a point. Let's say here's your point P naught, X naught, comma Y naught, comma Z naught. We're now in 3 space. Then if you wanted to go the shortest distance, right, D might be the length of this line segment from one perspective. It might look like that. And that would just be if this was maybe a horizontal, slightly inclined piece of paper, and you then somehow went directly towards that plane. That would be the distance there, the length of that line segment. And this point would be the point on the plane closest to P naught. Okay. Okay, so this is illustrating part B of that theorem. Illustrating part A. Okay, and so if you can see that the problem needs one of these formulas, then you can just take this formula and apply it to the problem, and you can find the distance that you need. Okay, and you can prove these two formulas, and then the proof is a little bit more sophisticated than just using it. But with the theorem, you can just use the formula. Okay. Okay, so example 7. So example 7 in 3.3 is find the distance, capital D, between the point -1, between the point -1, -4, -3, and the plane, 2x minus 3y plus 6c is equal to -1. Okay, that's a point, and we have a plane. Between now right here, point between that point and the plane. Okay, and so the solution, we can just apply our formula. So, from the formula in theorem 3.3.4, we know that our distance, capital D, between that point and that plane is of the form the absolute value of ax naught plus by naught plus cz naught plus d over the square root of a squared plus b squared plus c squared. Okay, so we just need to find the value of that expression. And so what we need to find, to just plug into that formula are the following things. One, we need to find what little a is, what little b is, what little c is, what x naught is. Oh, actually 4 is going to be what little d is, 5 is going to be what x naught is, 6 is going to be what y naught is, 7 is going to be what z naught is, and so, okay, and you just plug in those values. So we just need to know what those 7 things are for this formula, right? All right, but this is easy. The point here, this point, right? And so this point, -1, comma -4, comma -3, this is equal to x naught, comma y naught, comma z naught, right? Our point P naught in our formula here, when we have our plane, and then we have a point P naught, which is x naught, y naught, z naught, right? And then the distance, capital D here, between the plane and that point, right? And so that point, that given point here, the components are x naught, y naught, z naught respectively. And so this tells us that x naught is -1, y naught is -4, and z naught is -3. So here x naught is -1, y naught is -4, and z naught is -3. And then for A, B, C, and D, we have our plane. And our equation of our plane is ax plus by plus cz plus d is equal to 0. That's our equation of our plane. And so if our plane is given by 2x minus 3y plus 6z, and there's equals -1, I'm just going to add 1 to both sides, equals 0. And so this equation is an equivalent equation to the given one. That means that this equation has the same solutions as that one. And so I can use this equivalent equation instead of that one to find A, B, C, and D. And so here little a is 2, little b is -3, little c is 6, and little d is 1. Okay, little a is the coefficient of x, little b is the coefficient of y, little c is the coefficient of z, and little d is the constant at the end. Okay, so a is 2, b is -3, c is 6, and d is 1. And so those are the 7 values in that formula, and so you just plug that in. And so a is 2 times x naught, plus b times y naught, plus c times z naught, plus 1. That's the plus d at the end. I'm just going to write this over here. That's plus 1. There we go. And that's divided by the square roots of a squared plus b squared plus c squared. Okay? And so when you calculate that, this is the absolute value of -2 plus 12, which is 10. 10 plus -18 is -8, plus 1 is -7. So this is the absolute value, -7. Okay. Okay, in the book this is a 1. I'm going to keep that as -1. Okay, and then this is over the square root of 4 plus 9 plus 36. So that's 49. So this is 7 over 7, which is 1. Okay? And so the distance between this point and that plane is 1. Okay, I like that answer better. Okay. Okay, so let's keep going. So let's look at the next example. Okay. So in the next example, example 8. So in example 8, what we want to show, well, first we have the planes. So the planes x plus 2y minus 2z is equal to 3, and 2x plus 4y minus 4z is equal to 7. So those two planes are parallel. So first, let's see why they're parallel. First off, n1, which is the normal vector to the first plane. This is the first plane, the first one I wrote down. So the normal vector to the first plane is n1, and that's equal to 1, 2, -2. Those are the coefficients of x, y, and z respectively. N2, which is the normal vector to the second plane. This is the second plane. Okay, the second one I wrote down. And so now the normal vector to that is 2, 4, -4. The coefficients of x, y, and z respectively. Okay. Now, if those are the normal vectors of those two planes, let's look at the fact that this vector is 2 times that one. So 2, 4, -4 is equal to 2 times 1, 2, -2. 2 times 1 is 2, 2 times 2 is 4, 2 times -2 is -4. So this vector is 2 times this one. This is n2, and this is n1. And so this shows that n2 is 2 times n1. And so these two vectors are scalar multiples of each other. So this implies n1 and n2 are scalar multiples of each other. If two vectors are scalar multiples of each other, that implies that those two vectors, n1 and n2, are parallel. Okay? So if you have one plane, P1, goes out in all four directions. The plane continues in all four directions here. And then if you have another plane, P2, also going in all four directions. And if you find that the normal vector to P1, which I'm going to write over here, if you find that the normal vector to that plane is parallel to the normal vector of the other plane, then the two planes themselves are parallel. Okay? So do you see by the picture how these two normal vectors are parallel to each other? And you can think visually in your mind of how that means that the two planes should be parallel to each other. Okay? And so the fact that our two normal vectors are parallel, it means then that our two planes are parallel. So that implies that P1 and P2 are parallel planes. So showing that two planes have normal vectors that are parallel means the planes themselves are parallel. So that's P1 and that's P2. Okay. Okay, so we showed that those two planes are parallel. And then I'm just going to add to that in example 8. Next, I just want to find the distance between them. Okay, so x plus 2y minus 2z is equal to 3. 2x plus 4y minus 4z is equal to 7. Okay, so those are our two planes again. And so, okay, and so let's choose, let's look at this. Let's look at this plane, and let's choose the point P naught 3, 0, 0 in that plane. Okay. All right, all the points on this plane are points x, y, z that satisfy that equation. Well, if x is 3, y is 0, and z is 0, then that equation is true, right? And so it's easy to pick this point because if I want this expression to be 3, just make x be 3 and then y and z 0. And you'll get a point in that plane. Okay? So from our previous theorem, we know that the distance from a point on this plane to that plane is given by this formula, right? And so if we have one plane, P1 here, and we have another plane, P2 here, and they're parallel, and we find a point on P1, that's our P naught, and we find the distance between P naught and P2, then we found the distance between the two parallel planes. And that's because since they're parallel, it's an important fact to keep in mind in this problem, we showed these two planes are parallel. And so the distance between any point in this plane is the same from that. So every point in this plane is the same distance away from the other plane because they're parallel. And so by choosing a specific point on one plane and finding its distance to the other plane, I found the distance between the two planes. Okay? So again, every point on this plane is the same distance away from the other plane. And so all I need to do is pick any of the points on this plane and find its distance to the other plane. And then I found the distance between the two parallel planes. Okay? And so our P2 here, this is P2. Okay? So then it's the norm of ax naught plus by naught plus cz naught plus d over the square root of a squared plus b squared plus c squared. Okay, and then so the x naught, y naught, and z naught are this point. So x naught is 3, y naught is 0, and z naught is 0. And then a is 2, b is 4, 4, and D is -7. Okay, and so we get that because this equation here, 2x plus 4y minus 4z equals 7. We can rewrite that as 4x plus 4y minus 4z minus 7 equals 0. Okay, so then that's our equation there, right? Okay, so the D here is -7. The absolute value of A, which is 2, times x naught, which is 3, plus B, which is 4, times y naught, which is 0, plus C, which is -4, times z naught, which is 0, plus D, which is -7. That's over the square root of a squared, which is 2 squared, plus b squared, which is 4 squared, plus c squared, which is -4 squared. Okay, so just plug in all those values here. This is equal to the absolute value of 6 plus -7, your absolute value of -1 over the square root of 36. That's equal to 1/6. So the distance between those two parallel planes is 1/6. I chose a point on this plane and then used the formula to find the distance between that point and the other plane. It's 1/6. Okay, and so with that, we are done with 3.3. So that's the end of 3.3. Good. Okay, so 3.4. Okay, so theorem 3.4.1. Okay, so let capital L be the line in R2, R3. That contains the point x naught and is parallel to vector v, which is not equal to 0. Okay. Then the equation of the line through x naught parallel to v is x equals x naught plus 2v. That's equation 1. If x naught equals 0, then the line passing through the origin and the equation, its equation is x equals tv. And that's equation 2. Okay? So I'm going to box the two equations here. And I'm going to box the entire theorem. Okay, so this is theorem 3.4.1. It says let capital O be the line in 2 space or 3 space that contains the point x naught and is parallel to a non-zero vector v. And this is the equation of the line through x naught parallel to v. So what that means is if in 2 space, here's 2 space, and if you have the line L here, this is our line L, then let's say our line L contains the point x naught and it's parallel to v. So that means that this is the vector v with initial point x naught. Here's the point x naught, here's the vector with initial point at x naught in that direction. And so L goes through there, and you get that equation, right? So this is the line expressed by that equation. And so if I wanted any point on that line, let's say I wanted this point, x, on the line, then I would find that point x by taking x naught plus a suitable multiple of that vector v. So to get to this point on this line, I start at x naught, and I add a suitable multiple of that vector v to get to x naught, to get to x. Okay, good. Okay, so now, okay, and then in 3 space, you would just have a similar situation where if you had a line, here is line L, and you had a point x naught, and you had a vector v on line L, then the point x naught on the line and that vector going through it, then if you wanted to go to any point x on the line, it would be very similar. You would just start at x on 3 space, and you would add a suitable multiple of vector v and get to that point x on the line. Okay, and so this is a picture how an R2 and R3 equation 1 works. So in equation 1 in R2 it looks something like this, in R3 it looks like that. Okay, and maybe in this, and just pointing out equation 2, it's very similar. In 2 space, it would just be a line through the origin. And then if you had a point x naught on your line L, then if I wanted to go to a point x, it would just be, oh wait, sorry. If I just had a vector v here, if I had a vector v on line L, then going to this point x on the line L through the origin would just be a multiple of that vector v. And I would not need to add a vector x naught to it. It would just take any suitable multiple of one vector would get me to any point on the line. And so I could express it like that. And so this in R2, equation 2 is represented by that picture. Okay. In R3, you have 3 dimensions, one axis, another axis, another axis. You have x, y, z. You have a line L through the origin. And then if you had a point x, while you have a point x on that line, if you have a vector v on the line, then take a suitable multiple of that vector v and you get to that point x. And you don't need to add x naught either in R3 here because the line L is going through the origin. Okay? And so that's that theorem. So next, the next theorem is theorem 3.4.2. And let W be the plane in 3 space that contains the point x naught and is parallel to the non-collinear vectors v1 and v2. Then an equation of the plane through x naught that is parallel to v. V parallel to v1 and v2 is given by x equals x naught plus t v1 plus s plus x naught plus t1 v1 plus t2 v2. That's equation 3. Okay, so we have this equation here, and then if x naught equals 0, then the plane passes through the origin And the equation has the form x equals t1 v1 plus t2 v2. That's equation 4. Okay, so theorem 3.4.2, W is a plane in 3 space that contains the point x naught and is parallel to non-collinear vectors v1 and v2. Okay, so let me draw a picture of that so that makes sense. Okay, if you have, I'm going to draw the picture here. Okay, so let's say you have a plane here. So you have a plane here, and you have a point x naught on the plane. And then if you have 2 vectors, v1 and v2, that are parallel to the plane, okay, then this plane, the plane W here that I drew a picture of, you can get to any point x on the plane by starting at x naught, going a certain distance along v1, and then a certain distance along v2. Okay, so x, which is a point on plane W in 3 space, is equal to x naught plus t1 v1 plus t2 v2. Okay, this is a plane that's not through the origin. And so if the plane passes through the origin, you can get rid of the x naught and just add those 2 vectors. Okay. That's because if you're looking at this plane in 3 space, right, then if this plane is not going through the origin, here's the origin, right? We'll write a 0 there, or O. That's the origin. This is the x-axis, y-axis, and z-axis. If the plane is not going through the origin, I need to get to a point on the plane first. And so I need to move along the direction of x naught first. I need to go from the origin to x naught. And then I need to add a certain multiple of v1 and then a certain multiple of v2 to get to x. Okay? And then if the plane does go through the origin, here's the x-axis, here's the y-axis, here's the z-axis. Then there's the origin. Okay, so then the plane going through the origin there, then you just need 2 vectors parallel to the plane. And then that's v1 and v2. And so to get to any point x on the plane through the origin, just go a certain suitable multiple of v1 and then a certain multiple of v2. Okay, it's going through the origin in this picture. And so that's why you can use this as illustrating this equation, and this picture is illustrating that one. Okay? Okay, let's keep going. Okay, so the next definition is if x naught and v are in Rn, v not equal to 0, then the equation x equals x naught plus tv defines the line x naught parallel to v. Okay, in the special case x naught is equal to 0, the line passes through the origin. So if x naught and v are in n space and v is not equal to 0, then that equation defines a line through x naught parallel to v. Okay? And in the special case x naught is 0, the line passes through the origin, right? So this is our equation. And so here, the vectors are n tuples, okay? They're vectors with n components. They're vectors in n space. And so this x equals x naught plus tv equation, it would be, you're basically taking a point x naught in n space, and you're taking a vector v with initial point at x naught in some direction, and this is living in n space, not maybe 2 space, 3 space, 4 space, and then that's x naught, that's the vector starting it, it's not going in a direction, and then the line is going through that point and that vector. And that line can be in any n space you want. And so that equation will tell you how to get to any point on that line using x naught and the vector v. Okay? Right? And if this is not the, if x naught is not in the origin, I mean, if your line's not going through the origin, you need to have x naught in your equation, because again, you have to start at the origin, you have to get to x naught. And once you get to x naught, then you have to go somewhere on the point by adding a suitable multiple to vector v in the same direction as your line. Okay? So again, to get to a point x on your line, if the line does not go through the origin, you first have to get to the line. First have to get to some point on that line by taking the vector x naught on the line. So you get to a point on the line, x naught. Then when you get to a point on the line, you just have to get to another point on the line. And to get to another point on the line, just add a suitable multiple of a vector going the same direction, or maybe the opposite direction of line L. And then that multiple of v will take you from x naught to any arbitrary point x on the line. And so that's why you can represent your line as x equals x naught plus tv. You start at a point x naught in your line, and you add a suitable multiple of a vector in order to get to any other point on the line. Okay? Right? And again, if the point is not on the origin, then if you're living in n space, and I'm just going to use R3 as an example because it's easy to draw a picture of. If the line is going through the origin, this is the origin, then that's your line. And then just to get to any point on that line, just take a vector on that line. You're starting at 0, so you don't have to go. In the beginning, you start at 0. And you just add a suitable multiple of vector v and get to a point x, and you don't need the x naught in your equation. Okay? And right, and if the line passes through your origin there, right, x is equal to tv, and that's because x naught is 0. Okay? And so this picture, again, is illustrating the line passing through the origin. This picture is illustrating an arbitrary line, whether it does or doesn't pass through the origin. Okay, let's keep going. Okay, so okay, so let's keep going. So let's look at some examples. So the first example is find a vector equation and parametric equation of the line in R2 that passes through the origin. and is parallel the vector negative 2, comma 3. So find a vector equation, parametric equation of the line in R2 that passes through the origin and is parallel to that vector. Okay, so solution. So x equals tv, which equals a t times negative 2, comma 3, which is equal to negative 2t, comma 3t. Okay, so x is that vector there. Okay, right? Because we know since it passes through the origin and it's parallel to that vector v, then the equation has to form x equals tv. Right? And so v is just that. Okay? And so that means that we can say two things. We can say that the parametric equations are x equals negative 2t, y equals 3t. Those are parametric equations. Okay, so that's x and y. Now, the vector equation is x comma y is equal to t times negative 2 comma 3. And that's the vector equation. Okay, so we have the parametric equations and the vector equations. So these are the parametric equations, this is a vector equation. Because this vector is equal to t times that vector. This is the first component and second component, and so these are parametric equations. Okay, so this example is showing you how to find the parametric equations and the vector equation for this line. Okay, so this is one example of doing both those things. Okay, and now another example, part B of that same example, is find a vector equation and parametric equations of the line in R3 that passes through the point P naught 3 and is parallel to B equals 4, comma. So find a vector equation, parametric equations of a line R3 that passes through that point and is parallel to that vector. Okay, so it passes through a point and it's parallel to this vector. And so it doesn't say anything about going through the origin. So it may or may not go through the origin, but we don't know that. So we're going to use the equation x equals x naught plus t1 plus tv. Okay, so we're still talking about a line. Okay, so the fact we're talking about a line means that our equation is x equals x naught plus tv. X naught is our point. So x naught is equal to the point 1, comma 2, comma negative 3. V is equal to the vector 4, comma negative 5, comma 1. Okay, and just plug that into that equation. And so this is equal to x naught, which is 1, comma 2, comma negative 3, plus t times that vector 4, comma negative 5, comma 1. Okay, and so here we have a vector equation already. This is already a vector equation. That's because the things used in the equation are vectors. This is a vector, and that's a vector. Okay, so our vector equation is x is equal to this plus t times that. That's our vector equation. Okay, and then if you wanted the parametric equations, right? Find a vector equation. Do that here. If you want the parametric equations, just separate it by components. So 1 plus 4t, comma 2 minus 5t, comma negative 3 plus t. And so x is equal to that. Okay, so our vector x is equal to that. And so this is the x component, that's the y component, that's the z component. And so little x is the x component, which is 1 plus 4t. Little y is the y component, 2 minus 5t. And little z is negative 3 plus t. Good. So these are the parametric equations. So the parametric equations are those. Okay, good. Okay, so that's a vector equation. Those are parametric equations describing that line. Okay, so those are the parametric equations, vector equations describing that line in that example. Okay, and so now C, and so C, we're going to find 2 points on the line difference from P naught, which is 1, comma 2, comma negative 3. Okay. So let's just look at our parametric equations again. X was 1 plus 4t. Y is 2 minus 5t. Z is negative 3 plus t. Okay, so let's find 2 points on the line different from that point. Okay, right? So all this is doing is it's just telling you points x, y, and z on the line for values of t. So let's say t equals 1. If t is 1, x is 5, y is negative 3, and z is negative 2. Okay? And so a point on the line is 5, comma, negative 3, comma, negative 2. Okay? And then t equals 2. Then a point on the line is x equals 9, y equals negative 8, and z is equal to negative 1. So our point is 9, comma, negative 8, comma, negative 1. Okay, so this point is a point on the plane when t is 1, and this is a point on the plane when t is 2. And so we now have 2 points different from that point, right? Each of these points are different than that point. And so the goal was to find 2 points, and we found our 2 points. For any value of t, our parametric equations tell you a point on the line. And each value of t is a different point on the line. Right? If you plug in a different value of t here, you'll get a different x value. And once a point has a different x value, it means it's a different point. And so each different value t gives you a different point on the line. Okay? Okay. Okay, so now example 2. Find vector and parametric equations of the plane Okay, so we're going to find vector and parametric equations of this plane. Okay, and so to do that, okay, so we have this plane, and so we're just going to find a solution. So this is the leading variable, and these are the free variables. Okay, if you look at the corresponding augmented matrix, this is overkill, this is too much to do for this problem, but if you look at the augmented matrix, if you thought of this one linear equation, as a linear system, a set of linear equations, if you just thought of one as an entire system, and you found its augmented matrix, then this would be the leading one, right, of that row, right? And the leading one corresponds to the leading variable, remember? So this is, x is a leading variable. But then, since this is a leading variable, there's only one row, there are no other variables that correspond with leading ones. And so that means that this y and this z do not correspond with leading ones. And so this means y is a free variable, and z is a free variable. Neither of them correspond with a leading one in the augmented matrix representing your linear system. Okay, so y and z are free variables, and so when you have a linear system and you want to find its solutions, you set the free variables equal to parameters. So I'm going to set y equal to t, and z I'm going to set equal to s. So I'm setting each free variable equal to its own parameter. And then so you have your equation x minus y plus 2z is equal to 5. And then, so you plug in y and z. So then x is t minus 2s plus 5. So x is 2t minus 2s plus 5. And so now that is, we've represented this with parameters. Okay? And then, okay? So x is now written in terms of s and t. And so now the final solution would, in our parametric equations, with x equals t minus 2s plus 5, y is equal to t, z is equal to 5. I mean, z is equal to s. Okay, that's 5. This is s. Okay, this is s. Good. So these are the parametric equations describing that line. Okay, the vector equation you could find, I'm going to erase this because I wrote that already. So I'm going to erase just this part. And so to find the vector equations, well, x, y, z, a point on the plane, the x component is t minus 2s plus 5. The y component is t, and the z component is s. So here, there's 1 t here, 1 t here, and 0 t is there. This is plus s, which is negative 2 comma 0 comma 1. And then plus just the constant, just the constant vector here, 5 comma 0 comma 0. Okay. And so now this is the vector equation of the plane, saying x comma y comma t is equal to that. That's the vector equation of the plane. Okay, so we're representing our plane here with the vector equation, the same plane here with parametric equation. Okay, parametric equations are solving for the components of your vector, x, y, and z, in terms of variables, in terms of parameters. Okay, so we've solved for the components of points in the plane using parameters here, s and t. And here the vector equation is, we're building our equation from vectors. And so this is a vector, this is a vector, and that's a vector. And so it's t times one vector plus s times another vector plus another vector. So this is a vector equation because it's a vector made up of vectors and scalar multiples. T and s are just scalar multiples. Scalars, okay. Real numbers. Okay, so we found vector equations and we found parametric equations for that plane. So that's example 2. Okay. Okay, so now the next example, we're just going to find the vector and parametric equations of the line through the origin. Of R4 parallel to V, which is equal to 5, comma, negative 3, comma, 6, comma, 1. So find vector and parametric equations of the line through the origin in 4 space parallel to that vector. Okay. Since it's through the origin, we know that our vector equation is of the form x equals, this is a line. So it's a line through the origin. So this is x equals tv. Okay. So our equation representing this line through the origin is x equals tv. So what we need to find is just, so this is really easy. So then x is equal to t times that vector parallel to the line. 5, comma, negative 3, comma, 6, comma, 1. Okay, and so the vector equation is x equals t times 5, comma, negative 3, comma, 6, comma, 1. That's our vector equation. That's our vector equation, right? It's made of just t times that vector. And then if we want the parametric equations, multiply t, 5t, comma, negative 3t, comma, 6t, comma, t. And now the components, that's x component, y component, z component, and I can call that the w component. So this is the x component, the y component, the z component, and the w component. And so its parametric equations are x equals 5t, y is equal to negative 3t, z is equal to 6t, and w is equal to t. Those are the equations for those components, and so those are the parametric equations of this line. Okay, so now we have our vector equation here, and we have our parametric equations of the line here. Vector equation of a line, of that line. Okay, and so in part A, we're done with part A. Find the vector and parametric equations of a line R4. It passes through x dot, which is equal to comma, negative 1, comma, 0, comma, 3, and is parallel to both v1, which is equal to 1, comma, 5, comma, negative 4, and v2, which is equal to okay, so we're going to find the vector and parametric equations of a line in 4 space passing through that point and parallel to those two vectors. Okay, So it passes through this point, and it's parallel both to this vector and this vector. Through that point, parallel to those two vectors. Okay, so the solution is just x equals x naught plus t1 v1 plus t2 v2. Okay, and so that's from a previous theorem. That's how you find a point x in your plane. Right? Here's your plane. Here's your plane. Here's the point x naught in your plane, and let's say one vector v1 is here, another vector v2 is there. They're both vectors that are parallel to the plane. Okay. Okay, and so this is equal to x naught, that point, plus t1 times this vector plus t2 times that vector. Okay, and so then just solve for each component. The first component is 2 plus t1. The second component is -1 plus 5t1 plus 7t2. The third component is 2t1 minus 8t2, and the fourth component is 3 minus 4t1 plus 6t2. Okay, and so I just solve for all four components. That's the first component x, the second component y, the third component z, the fourth component w. Okay, and so in this notation, x is representing the entire vector. Little x could also represent now the first component of that vector x. Okay, the first component is the same letter as. Right, so I'm not saying that this x and x. I'm not saying this x and that x are the same. I'm just using the notation that x is the vector and x is representing the first component of it. It saves time. Okay, so then the parametric equations is x equals 2 plus t1, y is equal to 1 plus 5t1 plus 7t2, z is equal to 2t1 minus 8t2, w is equal to 3 minus 4t1 plus 6t2. Okay, so now I solve, and these are the parametric equations describing that line. So these are the parametric equations. Okay, so these are the parametric equations describing the line because I found this to be a point. And so x, y, z, and w are just the first, second, third, and fourth components, respectively, of a point on that line. Okay, so those are the parametric equations. The vector equation we already found. The vector equation was that this x is equal to that. X is equal to this vector plus t1 times that vector plus t2 times that vector. That's the vector equation. Okay, and so we found the parametric equations and the vector equation. X equals equal to that. And so that's part B. Okay, so if you're dealing with if you're thinking of n space, and you take the points x naught and x1, and so these 2 points are not equal in n space. Okay, so we're thinking of 2 points x naught and x1 that are distinct, different in n space. Then we can talk about the line determined by these points. Okay, so if the line L going through those 2 points in n space, This is a line determined by those two distinct points, and its equation is x equals x naught plus x1 minus x naught times t. So x equals x naught plus t times x1 minus x naught. That's equation 9. Okay? And so this equation tells you what the line L is, the only line L that goes through those two distinct points in Rn. Okay? Okay, so the vector starting at, this vector starting at x naught and going to x1, this vector, this is the vector x1 minus x naught. Okay, so x1 minus x naught is the difference of two vectors. It itself is a vector. So v equals x1 minus x naught is the vector that starts at x naught and then goes to x1. Okay? And so if you want to take a point x on your line, if you want to get to a point on your line, just like before, if you're in n space, you start at the origin, you get to x naught. You start with x naught, you get to a point on the line, then you add a suitable multiple of x1 minus x naught to get to any other point on the line. Okay? Okay, if you simplify this equation, you could also write it as x equals 1 minus t x naught plus x1. That's equation 10. Okay. So x equals 1 minus t times x naught plus x1. Okay, this is an equivalent equation to that one. It has the same solutions. Okay. Okay, if you want to see how I did that, x is equal to x naught plus t times x1 minus x naught. That's equal to x naught plus tx1 minus tx naught. Factor out the x. I'm going to move around the terms. This is x naught minus tx naught plus tx1. That's equal to x naught times 1 minus t plus x naught plus x1. Sorry, this is plus tx1. That's plus tx1. Sorry, this is tx1 plus tx1. Okay, and so there we go. So now we have that x is equal to x naught times 1 minus t plus tx1. Okay, and so these are called two-point vector equations. Of a line in Rn. Okay, so these are two-point vector equations of a line in Rn. Okay, another example. Find vector and parametric equations for a line in R2 that passes through these 2 points. Good. Okay, so find vector and parametric equations for a line in. So find vector and parametric equation for a line R2 that passes through those 2 points. Okay, so the solution is we're just going to use the same equation as before. So x is equal to x naught plus t times x1 minus x naught. Okay? I like this one better because I can visualize how it works better this way. Okay? So here, x naught, you can think of x naught as the point 0, 7, and x1 as the point 5, 0. Okay, and you just plug that in there. So x dot is 0, 7 plus t times x1 minus x naught. So what's x1 minus x naught? It's this vector minus that one. That's equal to 5, negative 7. Okay, so x1 minus x naught is 5, negative 7. This is 5, negative 7. This is equal to now, so here we already have the vector equation. X equals 0, 7 plus t times 5, negative 7. That's the vector equation. We're done there. Okay? And then this is the same as 5t, 7 minus 7t. Solving for each component. And so the parametric equations would be, this is the first component x, this is the second component y. And so the parametric equations are x equals 5t, y equals 7 minus 7t. Okay, so these are the parametric equations, and that's the vector equation. Right, so writing it out here, x equals 0, 7 plus t times 5, negative 7, that's the vector equation. Okay, so now we found both the vector and parametric equations in this example. Okay, and so we're done with that example also. Okay, so definition. Definition is if x on x1 are in vectors in n space, then the equation x equals x naught plus t times x1 minus x naught from 0 less or equal to t less or equal to 1 defines a line segment from x naught to x. When convenient, (13) can be written as x equals 1 minus t x naught plus t x1. And again, t is between 0 and 1 inclusive. Okay, so there's our definition. So this equation defines a line segment from x naught to x. This is equation 13, and this is equation 14. And those equations are only considering t values between 0 and 1 inclusive. Okay, and so a picture of this would be, here's the point x naught. Here's a different point x1. They're in n space. This is the line segment connecting one point to another point. X naught, corresponds with the value of t equal to 0. And this point x1 corresponds with the value of t equals 1. And so as t goes from 0 to 1, our point in the line goes from x naught to x1. So you can describe any point on this line segment, starting from x naught ending in x1. We can take any point x, we can write it as x naught plus some value of t between 0 and 1 inclusive times x1 minus x naught. And this is just an equivalent equation to that one. Okay. This is just another way to say that. Okay, that's the picture that describes the situation. Okay, so let's see this. Let's see this in action. Let's look at this example. So the example is the line segment in R2 from the point x naught equals 1 comma negative 3 to x1, which is equal to 5 comma 6, can be represented by okay. So again, our equation is x is equal to x naught plus t times x1 minus x naught. And so it tells us what x naught is, and it tells us what x1 is. And the parameter t is between 0 and 1 inclusive. So you just plug this in. X naught is that vector, and times x1, which is this, minus x naught, which is that. So this is x1 minus x naught. Okay, that's this part. So this is equal to 1 comma negative 3 plus t times 4 comma 9. This vector minus that vector. 5 minus 1 is 4, 6 minus negative 3 is 9. And then, so that's one way to represent it. And so we can represent it like that. So therefore, our vector x is equal to 1 comma negative 3 plus t times 4 comma 9. Okay. So that is a representation of that line segment. And again, t is between 0 and 1 inclusive. Okay, so that's that example. Okay, so a linear equation in the variables x1 to xn has the form a1 x1 plus a2 x2 plus dot 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 plus an xn is equal to b. Okay, so this is a linear equation in those n variables, right? The n variables are x1, x2 to xn, each with its own coefficient and equal to some constant b. The corresponding homogeneous equation is a1 x1 plus a2 x2 plus dot 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 plus an xn is equal to 0. Right? A homogeneous equation is one where it equals the constant 0 instead of an arbitrary, and instead of any constant. Okay, so this is equation 15 in this section, and this is equation 16. And so if we're letting vector A equal to the vector A1, A2 to AN, and the vector X equal to X1, X2 to XN, we get that A dot X equals B represents equation 15. So if this is your vector A and this is your vector X, then dotting this vector with this vector gives you the left side of this equation. This vector A dotted with this vector X gives you the entire left side of this equation, and it's equal to B. And then A dot X equals 0 represents equation 16. So this equation 16 is A dot X, which is the left, this left side is A dot X, that's A dot X, and it's equal to 0. And so this is equation 17 in this section, and this is equation 18. Okay, so this is equation 17, this is equation 18. This represents 15, this represents 16. And so you can write more succinctly this long equation by just A dot X equals B, or A dot X equals 0. Okay. Okay? Okay, so theorem 3.4.3. If A is m by n, then the solution set of the homogeneous linear system AX equals 0 consists of all vectors in Rn. That are orthogonal to every row vector of A. Okay, so this is theorem 3.4.3. So if A is m by n, then the solution set of this homogeneous linear system AX equals 0 consists of all vectors in Rn that are orthogonal to every row vector of A. Okay, so what in the world am I talking about, right? Okay, so what's happening here is that if you have this let's say this is our vector. I don't want to run out of marker. That's vector A. This is vector X. This is m by n vector A. This is n by 1 vector X. And A times X is equal to 0. In this case, the 0 vector is the m by 1 0 vector, right? The inner entries correspond n, and the outer entries determine the size of the product. So that's m by 1. That's the size of the AX. It's the m by 1 column vector. Okay. So what this theorem is telling you is that if A is m by n, then the solution set of all the possible n tuples, all the possible column vectors I could put here, where A times that would be this 0 vector. Okay, so the solution set is all possible vectors I could plug in here into this equation where it holds, where it's true. Okay? Vectors in Rn, right? So the solution set is made up of vectors in Rn. It's made up of vectors with n components. And it's this vector in n components is described as a column vector. As a column vector. Okay? So it says that the solution set is all the vectors in n space that are orthogonal to every row vector of A. So the reason why, hopefully this makes sense, is if you take the first row vector is the first row of this matrix. This is R1. That's R1, that row vector. The second row of A, that's R2. The third row would be R3. And then let's say we take the nth row, that's Rn. And so the rows of A are the row vectors of matrix A. Okay? If we have a solution to this linear system, if we have a vector we can plug in here into this equation, that would mean that I could take a row vector here, dot it with this, and get 0. Okay? So in order for that to make sense, you have to think, how do I get the first 0 in this equation? How do I find the value of this matrix at this component? You would take, this is the first row and the first column. I would take the first row of A and then dot product it with the only first column of X. And so R1 dotted with this equals 0. The fact that this component is 0 means that the first row dotted with that vector X is 0. The fact that the second component here is 0, that means R2 dotted with X is 0. And continue, Rn here dotted with X is 0. So that equation, this equation tells us, implies that the first row dotted with our solution x is 0, the second row dotted with x is 0, and so forth, up to including the nth row of A dotted with x is 0. And so if all of the rows of A dotted with our solution x is 0, that means that our solution x is orthogonal to every row of A. That implies that x is orthogonal to every row of A. What we did was we showed that if we took a solution x and we dotted with any row of A from R1 to Rn, oh, it's m by n, there's m rows. This is A sub m1, A sub m2, A sub m3, A sub n. So that's the mth row, and then this is R sub m. Okay, so you take the m rows, each row vector, and you dot with x, you get 0. So that x is orthogonal to every row A. Right? The two vectors are orthogonal. It's the same as saying their dot product is 0. Okay? So each dot product is telling you that x is orthogonal to each row. Okay? And so that's one direction, right? We're showing that a solution to this equation is orthogonal to every row of A. So every solution, so a solution implies orthogonal to every row. Okay? If you have a solution to this linear system, then it's orthogonal to every row. If you have a vector that's orthogonal to every row, that would imply, if you had a vector here that was orthogonal to every row, that would mean this vector dot product with each row vector would be 0. That would mean that this vector satisfies this equation. That would mean that this vector is a solution. That implies you have a solution to your system. Okay? So having a solution implies that the solution is orthogonal to every row of A. Having a vector orthogonal to every row of A implies it's a solution. And so the solution set of this linear system is the same as the set of all vectors orthogonal to every row of A. Okay? That's determined by this if-then statement and that if-then statement. Okay? A vector, one more time. A vector being a solution means it's orthogonal to every row of A. A vector being orthogonal to every row of A means that it's a solution. And so that means the set of all vectors orthogonal to every row is the same as the set of solutions. They're the same thing. Okay? Okay. So look at this for a while. Okay. Okay. Okay, so theorem 3.4.4. The general solution. So the general solution of a consistent linear system AX equals B can be written as can be found by adding any particular solution of AX equals B to the general solution of AX equals 0. So the general solution of a consistent linear system AX equals B can be found by adding a particular solution of AX equals B to the general solution of AX equals 0. Okay, what does that mean? Okay, you start with your linear system AX equals B. Okay, here's X naught. it's a particular solution. Okay, x naught is a particular solution to ax equals b. It's a vector x naught. I can plug into x there and the equation holds. Okay, that's step one. Then, what do you do next? Take the equation ax equals 0. The video's almost over. Ax equals 0. Find the general solution. Find the general solution to ax equals 0. Then, x naught plus the general solution. X naught plus the general solution. That's the general solution to ax equals b. Okay, so again, if you start with ax equals b, x naught is a particular solution. Then take x naught, ax equals 0, find a general solution for that. Then take the particular solution of this, add the general solution to that. This entire expression is a general solution to ax equals b. Okay, so that's like step 1, step 2, step 3. That's what Theorem 3.4.4 is saying. Okay, break it down to these 3 steps. Step 1, find a particular solution of that. Step 2, find a general solution of that. Step 3, x naught plus that general solution is a general solution to ax equals b. Okay, and so that is the end of 3.4. Okay, so that's the end of 3.4, and next time we will talk about 3.5. Okay, bye.